So we will continue from our previous class. Now, if we return back, we had an element node 1, node 2. This is element 1. Over here on this element, we were having force R, and here we have force F. We'll first write down the element stiffness matrix, that is AEYL into 1 minus 1 minus 1 1. We'll also note down the nodal displacement matrix. Here we had U1 and U2, and we'll also write down the F vector, F matrix, then that was L Txy2 1 1, and Q matrix is equal R and F, and because we know the first term we had was fx1 and this is fx2. Fine. So as we write the expression, it is the fundamental equation in front of us is it is Ka minus F is equal to Q. So we'll write AE by L 1 minus 1 minus 1 1 minus F, that is LT by 2 1 1 is equal, and it's also in multiplication with this one. So we have this is in multiplication with U1 and U2 minus LTX by 2 1 and 1 is equal R and F. Okay, since if we look at this problem, it is fixed over here, so it's quite evident that U1 is equal to 0. So for us, the value of U1 is equal 0. So if we substitute the value of U1 to be equal to 0, we will obtain AE by L into minus U2 minus LT by 2 is equal to R, and AE by L into U2 minus LT by 2 is equal F. Okay, so these are the values of the R and F that we will obtain from while we solve this equation Ka minus F is equal to Q using the finite element analysis. We can further write an expression about the displacement. U is equal U1 N1 plus U2 N2. Since U1 is equal to 0, therefore U becomes equal N2 into U2. Okay, from this equation we can calculate the value of U2. U2 can be written as F plus LT by 2 into L by AE. So we can write this is equal, the total displacement is equal to N2 multiplied by F plus LT by 2 into L by AE. This is the value of their displacement. We can also calculate the value of the strain. E is equal du by dx, that is equal F plus LT by 2 into L by AE, and the derivative of N2 is equal to 1 by L. So that will be equal to F plus LT by 2 into 1 by AE. That is the value of strain. If we are asked to calculate the stress, that is E, Young's modulus of elasticity times the strain. So this expression, if multiplied by E, that E and E will cancel. This gives us the value of then stress. Okay, so this is so quite important expression is stress is equal to twice F plus LT whole divided by 2 times A is equal to sigma. Now for us, if we say that T is equal to 0, then sigma becomes equal to F by A. That's what's already known. Okay, so this is how we can make use of finite element analysis to calculate the value of U and all expressions. Now, let us return back to our analysis. Now we know the value of K, we know the value of A and other fundamental equations. But we have done the entire analysis for one element only. We have taken only one element into consideration. Now, say for example, we talk about two elements. So how does the finite element analysis solve a bar problem where we employ two elements? That's what we will try to do. We'll try to solve. One thing is the analysis that we have done right now. This analysis can be used for two elements. We will the analysis that we have right now done for one element, we can repeat it for two elements. And another thing is to directly use the stiffness matrix and the nodal matrix to find the values of the displacements and other things. So let's directly write down the equations. That will save a lot of time for us. So let us write it. Let's suppose we are having a bar. Now this bar is composed of two elements. So this is element 1, this is element 2. This is node 1, this is node 2, this is node 3. On node 3 we are applying force F, and node 1 we are having force R. And be careful about this node 2. This is an internal point. The summation of all the forces on this node has to be equal to 0. Okay, so first of all, take node 1 into consideration, right? The stiffness matrix for node 1, that will be AE by L, 1 minus 1 minus 1 and 1. Write down the displacement matrix A for element 1, that will be U1 and U2, and write also the force matrix for it. Okay, and the force matrix is F is equal, let's suppose some traction is acting on it, or that is LT by 2 1 1. And what are the Q vector? That is force acting at node 1, that is R, And once you are segregating these two, let's suppose there's force F from 2 to 3. Let's suppose this F1, okay? That's F1. Okay. And now write down the so okay, this is fine. We're happy with it. We don't have an issue. Similarly, write for this element 2. For element 2, we will be having the same stiffness matrix as for this, because A is constant, we're assuming E to be constant, length to be constant. Even if they are same, still we'll be having it AE by L, 1 minus 1 minus 1, 1. Okay. And we'll be having A now for element 2. The nodal displacement matrix will be U2 and U3. And F will be equal LT by 2, 1, 1. And as far as Q is concerned, the Q matrix will be equal F. Now, you have this element into consideration. So we'll write this as F1 prime and F. Okay. Because here, when you are segregating this element, this force on this element will be because of the element 2. Okay. Now, when you are taking element 2 into consideration, force on it, node 2 will be because of node 1. Okay. So that's why I'm writing it as F1 and F1 prime, where F1 and F1 prime are having same magnitude, but they're opposite in direction. Okay. Now we'll write the total. We'll assemble these two matrices. We have to assemble the matrices. Okay. So this is a step that is known as the assembly. Assembly is very important. Okay. So how do we assemble? The one is, so how many nodes we have? We have 1, 2, and 3 nodes. So we will have to write it in the way, let me write it over here. We change the color. We'll write it like K A minus F is equal to Q. This is for total, okay? For the total composed of 2 elements. Okay. So how many nodes we have? We have 3 nodes. Okay. So what we will be doing, first we'll be writing a matrix. I don't know. Let me put it blank. And in this matrix, I don't know, let me for some time forget how many elements I'll be having. Okay. Let me talk about this A. What is A? A is the nodal displacement. So we'll be having U1, U2, and U3. So we'll write this as U1, U2, and U3. Minus the F matrix. What's F matrix? That is LT by 2. Okay, so it will be, let me write it like this, minus LT by 2. When I have 3 nodes, I'll be having 1, 1, 1. Okay. Is equal the external force matrix is. So it is force at node 1, force at node 2, force at node 3. That is R. And I will write here 0 and F. Why R, 0, and F? Because this is an internal point here. The sum of all the forces will be equal to 0. Now look here. So you'll be having, let me rub this face for 2 elements. Here we'll be having U1, U2, U3, right, like this. So first element is U1, U1. So here you have U1 and U2. Okay. Here you have U2 and U3, right, like this. So U1, 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 this is U1, U2 also. This is U2, U3. U1, U1 is 1. So we'll write here 1. Okay. The second element is U2, U1. So you have U2, U1 is here. So it's -1, we'll write -1. Then you have U3, U1. So U3, U1 is no element over here, so we'll put a 0 over here. Okay, now we have U1, U2, U1 and U2. Okay, so this is U1 and this is U2, that is -1, so we'll put a -1 here. Then the second element is U2 and U2. So U2 and U2, the U2 and U2 is coming from two sides. U2, U2 here is 1, so we'll write 1. But you are also having U2, U2 here as 1, so we'll place 1 plus 1. Okay, then you have U3, U2. Okay, U3, U2 is -1, so we'll write a -1 here. Okay, then you have U1, U3. That the no element is U1, U3, so we'll put it 0. Second is U2, U3, U2, U3. So U2, U3 is equal to -1, so we'll write a -1 here. And the last element is U3, U3, that's equal to 1. Okay, so we'll get the total stiffness matrix as 1, -1, 0, -1, 2, -1, 0, -1, 1. Okay, is this matrix symmetric about the diagonal? Yeah, I think it's a symmetric. Okay, N2. So let me write it over here. So we can write this. This is 1, -1, 0, -1, 2, -1, 0, -1, 1. And multiplied by U1, U2, U3 minus LT by 2, 1, 1, 1 is equal R0F. So this is the total matrix equation, FEM equation. Okay, we know U1 is equal to 0 because this point is fixed. So from this equation, we can calculate R and F in terms of U1, in terms of U2 and U3. So this is how. In fact, you can divide the entire problem into 4 elements. Okay, so you can have 4 elements. 1, 2, 1, 2, 3, and 4. Write down the individual stiffness matrix. Okay, so once you write individual stiffness matrix, you'll be having node 1, node 2, node 3, node 4, and node 5. So therefore, the K matrix, the total stiffness matrix, will be a 5 cross 5 matrix. Okay, in the same way, this procedure is to be continued. That's one thing. Number 2 is an important concept, that is writing the entire equations in terms of what you call as the matrix equation. We write the equations in terms of the matrices. That is something that we should try to discuss. What is the concept of writing the matrix equations? Okay, matrix formulation of the finite element equations. I hope that we will pick up in the next slide. Okay, so thank you.